right, guys, this is going to be our first online lecture, so hopefully it goes well. I've realized as I've been watching these videos of myself that my voice is very monotone, flat, very exciting, so good luck with that. Last time we were talking about phase diagrams, so you should be able to see this slide right here now. The phase diagram, right, basically always looks the same. On the y-axis over here we have our pressure, and on our x-axis down here we have our temperature. And so now we have these different sections of our phase diagram. So let's ask which phase goes where, right? So the solid always goes up here in the top left. The gas always goes down here in the bottom right. And then this middle section right here is our liquid, okay? Now let's talk about these red lines in here and ask this question right here: which lines correspond to which phase changes, right? So first, between solid and liquid, we have melting. If we're going from solid to liquid, we are melting across this red line. Going from liquid to solid is freezing, right? And then along this line here, this is the divide between gas and liquid. Going from a liquid to a gas would be vaporization. Going from gas to liquid would be condensation. Down here, in this small little area between solid and gas, we have sublimation. So if we're going from a solid to a gas, that's sublimation. And if we're going from gas to a solid, that is deposition. Right here, in between the solid, liquid, and gas is our triple point. If you'll remember last time we watched a video of a chemical where we lowered the pressure and the chemical was both boiling and freezing at the same time. And that's at this triple point right here. So this is the intersection of solid, liquid, and gas. And if we come right up here, we have our critical point, right? And above this temperature and above this pressure, we get our supercritical fluids, okay? Now, if you have any questions about any of that, feel free to email either me or the TAs with questions. So we should all be available to answer any of those, okay? Now, what happens when you increase the temperature at a constant pressure? So what that means is we're gonna come up here on this y-axis and just pick a point. And let's see, oh, I was really close. So let's say we pick a point at 0.63 atmospheres. So this is about the pressure in Denver, Colorado. And let's just increase the temperature. We'll start at 0 and we'll just increase on over here. As we increase from 0, we'll hit a point where we cross this melting freezing line. And this is where our substance will melt. So this is our melting point. As we continue on, we'll hit this other red line that separates vaporization and condensation. At this point, this is our boiling point, or our boiling temperature. Now what happens when we increase the pressure at constant temperature? Okay, so we'll just come over here and pick a temperature. Oh, not so close on that one. And let's increase the pressure. So at low pressures, most things are gases, even if they're very cold. At very low pressures, this is what outer space is like. Everything's a gas and it's just nebulous and floating around. And as we increase this pressure though, our gas is going to condense into a liquid at some point. And as we continue to apply pressure, our liquid will eventually become a solid. Now, this is true for most chemicals, that if you increase the temperature, or sorry, increase the pressure far enough, you'll get your substance to become a solid. Okay. For most species, they have a solid that is more dense than a liquid. However, for some species like water, that's not true. So for most species, this boundary between the solid phase and the liquid phase slants to the right. So if it slants to the right, that means that your solid is more dense than your liquid. But for water, since water has a more dense liquid than a solid, its boundary here between liquid and solid actually slants to the left, leans to the left. What that means, though, is if you increase your pressure without changing your temperature, you can actually get your ice, you can actually get ice to melt by applying pressure to it. So this is why at the bottom of the ocean, like in the deep trenches in the Pacific Ocean, where the temperatures are way, way, way below 0 degrees Celsius, you're actually not getting ice because the pressure is too high down there for ice to form. And so you're just getting liquid water at super cold temperatures. Right? So now, why is CO2, frozen CO2, called dry ice? This will get us into another point that we need to make here. So this is the phase diagram for CO2. You'll notice right here on the y-axis, which is pressure, at 1 atmosphere, if we increase our temperature here, it starts out at a solid at super low temperatures. And as we increase our temperature, we become a gas without ever passing through a liquid phase. So at higher pressures, yeah, we can get into a liquid phase, but at atmospheric pressure, CO2 is never a liquid. So what that means is that at atmospheric pressure, this dry ice sublimates, turns into a gas without ever becoming wet. So then we call it dry ice. Okay? So this actually brings up, though, a point about what is known as normal melting points. So CO2 actually does not have a normal melting point. Normal in chemistry terms means at 1 atmosphere of pressure. So most species at atmospheric pressure have a normal melting point, which is the point at which it will melt, the temperature it will melt at 1 atmosphere of pressure, and they will have a normal boiling point. And that is the boiling point, the temperature at which it will boil at 1 atmosphere of pressure. So now we've defined 3 different temperature and pressure values. So there's standard temperature and pressure. So standard temperature and pressure is 1 atmosphere, 0 degrees Celsius. Normal pressure means 1 atmosphere. And then we also have room temperature, which means 25 degrees Celsius. Okay, so make sure you have all of those logged away. Let's jump through the rest of this stuff. Just because we've covered it all. This is just going over the difference between pressure, or cooking at high pressure and cooking at low pressure. I will show you a quick little video here that's kind of fun.
In the flask is water heated to about 55 degrees Celsius, well below water's normal boiling point. We use a device to evacuate the air from the flask. The water boils, though its temperature remains at around 55 degrees.
That's just kind of a fun video, though, showing you how you can dramatically decrease the boiling point of water by dropping the pressure. So we'll jump through the rest of this real fast. All these slides are posted under lecture 28 on the content section, so if you want to go through and review it a little better, you can. All of the slides that I go over in these videos will still be posted just like normal. Okay. Now let's talk about vapor pressure and boiling point and how those compare, right? So stronger intermolecular interactions are going to make molecules want to stick together better. So that is going to make it harder to boil these species. So stronger intermolecular interactions equals a higher boiling point, right? We're going to jump through this iCLICKER quiz here and just ask, will a liquid with a higher boiling point have a higher or lower vapor pressure at a given temperature? Now, the way we're going to do these iCLICKER quizzes going forward, since we're not actually doing them, is I will just talk through them, talk through the logic here, right? So if molecules are more sticky, so they have more intermolecular interactions, you're going to have a higher boiling point because it's going to be harder to pull these things apart, right? But if you have high intermolecular interactions, you're also going to have a lower vapor pressure. So what that means is that a higher boiling point means a lower vapor pressure, right? These two things are the same thing happening. So we have molecules sticking together. If they stick together, they're not going to turn into a gas nearly as well. So you're going to have a lower vapor pressure. And since they're sticking together better, it's also going to be harder to boil them. So higher boiling point, lower vapor pressure. Okay. Now let's just talk quickly about moving through a phase diagram one more time. So this time we're going to go with CO2 at a higher pressure. We're going to go at 25 atmospheres, and we're going to just walk through this phase diagram here from negative 100 degrees Celsius, which is our 0 point on here. So we're starting at negative 100 degrees and going up, and we'll go up to 200 degrees Celsius. On this plot, you'll notice that the temperature is spaced at 20 degrees Celsius intervals, but the pressure is a little different. So we're starting at 0.1 atmospheres, then going to 1, then 10, 100, and 1,000. So these are increasing by increments of 10-fold rather than a set value. And this is what's called a logarithmic plot. So on this kind of plot, 25 atmospheres is actually right up here, pretty close to 100. But if we start here at really low temperatures, since we're at a high pressure of 25 atmospheres, this guy is going to be a solid. And as we heat him up, eventually this CO2, this dry ice, is actually going to go through a liquid phase. So it's going to melt. And then as we keep heating this up, eventually we will hit our critical point. We're actually just slightly under the critical point because the critical point requires 73 atmospheres. So we're a little below that. But we will skirt right underneath it and become a gas right over there, okay? So you'll want to get really familiar with how to move through these plots, how changing temperature, how changing pressure is going to affect which phase you're going to be in, okay? Now let's just finish with 2 iCLICKER quizzes. The quiz here is just going to ask which of these species is going to have the highest boiling point. So we have pentane here, which is just 5 carbons in a straight chain or a non-branching chain. We have 2-methylbutane here, which is a 4-carbon chain with 1 methyl group branching off. And then we have 2,2-dimethylpropane, which is a 3-carbon chain with 2 methyl groups branching off. Then we have 2 more options here. We could say they all have the same boiling point, or we can say it's not possible to predict their boiling point orders, okay? Now, what we have to consider here is the intermolecular interactions here. So we don't have any dipoles, no polar bonds in any of these molecules. We don't have any ions. So all we're going to be dealing with here is van der Waals interactions or London dispersion forces. You'll remember those are the same things. And so then we got to think which of these is the biggest. Well, each of these has 5 carbons, and they also each have 12 hydrogens. So don't forget the hydrogens branching out here that we haven't drawn for simplicity. So the formula for each of these is C5H12. So they're all the same size. Now we got to ask, how does shape play into this? So pentane here is a long carbon chain, which means that the 2 long chains have plenty of surface area to stick on top of each other. Whereas this guy down here, it has a tetrahedral geometry around this central carbon, and then each of these carbons branching off of it has a tetrahedral geometry around it with hydrogen. So this is basically a big old fuzzball. So the fuzzball, you have 2 fuzzballs, they're going to interact a little, get a little van der Waals interactions, but not nearly as much as 2 long chains. Okay, so the pentane is going to have the highest intermolecular interactions. And that means it's going to be the hardest to boil. And so pentane is going to have the highest boiling point, 36 degrees. And this 2,2-dimethylpropane is going to have the lowest at 10 degrees Celsius. All right, now let's ask which has the highest vapor pressure at 0 degrees Celsius. Okay, these are all liquids at 0 degrees Celsius. This is below all of their boiling points. But this is a very similar question. We're still just asking which has the strongest intermolecular interactions and which has the weakest. So pentane has the stronger intermolecular interactions. 2,2-dimethylpropane is going to have the weakest. So which of these is going to affect the vapor pressure? Well, specifically when we want to know which has the highest vapor pressure, well, pentane has those strong intermolecular interactions, so it's going to stick together better, which means it's going to have the lowest vapor pressure. 2,2-dimethylpropane, since it is going to stick together the least, it is going to have the highest vapor pressure. All right, now hopefully that is useful for you, and if you have any questions, feel free to either let me or the TAs know, and we will try and get back to you as best we can. Thanks, and stay healthy.